In this lecture, we will learn QAM Modulator. So our topic is QAM Modulator, and we have already gone through. We started the QAM modulation in the previous lecture. So we will see the in this lecture we will see the modulator at block level. So we will see the block diagram of a QAM modulator, which is shown on the screen. I'll explain each and every step. So we will move forward to find out the stepwise operations in each branch. So we have two branches, if you see in this diagram, and we will see how what operations are carried out at each step at the output of each block. So we will be interested in finding out the input of each block and the output of each block for a QAM modulator. And then for the proof of our concept, we will move towards the simulation model, and the simulation will be a code will be given for octave. So I'll give you the code for octave. You can also try this one in MATLAB. Very similar instructions are found in both. So we start with the QAM modulator, and if you let me write its expression as you are familiar with the modulator. So if we see the QAM, this is actually, let me bring the block diagram on the screen and I'll write its expression. So you are familiar with the expression of the QAM modulator from my previous lecture. So if I just write it, the symbol or the signal for QAM modulation SI of t, you can write it in this form: AI P of t and cos of 2 pi f c t plus theta I. So each symbol I, each SI of t, or each signal, QAM modulated signal, is identified by these two parameters, uniquely identified by these two parameters. So AI, the amplitude, and the phase, these two should be unique. This pair should be unique for each SI of t. Now if you observe this equation, you can rewrite it in this form. You can rewrite it as S1 of t cos of 2 pi f c t minus S2 of t sine of 2 pi f c t, sine of 2 pi f c. So you can rewrite this equation as a linear combination of two orthogonal signals, the cos carrier and the sine carrier, and the frequency is fc for both. So the frequency is fc for both of these carriers. So we have two orthogonal carriers at the same frequency. Well, I hope you can easily find this S1 of t and S2 of t, and if you just with a little bit of mathematical identity, if you apply your mathematical identity here, you can just cos of alpha plus beta. We applied cos alpha plus beta to this one, right? We applied let me move it to the center of the screen. So we actually applied cos alpha plus beta to this one. So you can rewrite it in this form, and if you observe closely, S1 of t, actually you can let me rewrite it. Let me open it for you so that you do not confuse yourself. So this is A P of t, and then you have cos of, or instead of writing the whole equation, let me just rewrite the s1 of t and s2 of t, right? Because we need s1 and s1 of t. Cos of 2 pi f ct can easily be seen here. So if you just write s1 of t, I can specifically write it should be equal to ai p of t, and then see you have sine of theta I. So this is your s1 of t. If you closely observe your s1 of t, this is your s1 of t from just by comparing it with this above equation, right? ai p of t sine of theta I. Similarly, you can rewrite your s2 of t, and you can say that okay, my s2 of t from the above equation is ai p of t and sine theta, right? So this is your s2 of t. Now we can further rewrite this s1 of t and s2 of t as a linear summation, as a summation of this this p of t. Let me rewrite it, and then I'll tell you as how do we rewrite it. I'll just combine this if you observe closely, but ai sine theta I, what is this? And similarly ai sorry, this should be cos theta I, right? This should not be sine theta I. This should be cos theta I. Let me rewrite it again. This should be cos theta I. So this is actually cos theta I. Let me write it. This is actually this is cos theta I, right? So this ai cos theta and ai sin theta I, p of t is common in both, right? So if we observe here, ai cos theta I is actually the image of I over psi 1, right? We can write it ai1. We write it ai1, and then it is p of t. Similarly, we can write the other one ai sin theta I as ai2 p of t. This is the image of ai over the second orthonormal basis function, or over the sine 2 pi f ct, the image of ai over sine 2 pi f ct. Now if you observe this these s1 and s2, if you observe this s1 and s2, when we say we can rewrite it in this form, it means we can just to be this is just for one time interval, right? So our s1 and s2 for between, this is for the time interval 0 to capital T, right? 0 to capital T. If we want to generalize this, because we just in the data usually will be like we have many bits to transmit. So if we generalize it, and for these different bits we just select some symbols. If you recall your previous knowledge, previous knowledge, what we did that, okay, we have our signal points. We have these signal points. Suppose this is, I'm drawing this for M16, so it's a 16 array, 16 array QM symbol, M array, right? So 16 array QM. So in 16 array QM, you have this. This is the constellation of 16 array QM. So the signal, we have many bits. Usually the bits are in, you can say, okay, we have a sequence of bits which we need to transmit, and we don't know what is actually the combination. Now we have these like we have these 16 unique signal points, and each signal point with each signal point, for example this one or any other one, we can send 4 bits. It represents 4 bits. So we can group our data into 4 bits, or we call it, we group our data into n tuples. This is also known as n tuple. So each n tuple is of n bits, and this n is equal to log m to the base 2. So each n tuple has n number of bits, log m to the base 2. So each n tuple contains n bits. Because we have m16, so we will have a group of 4 bits, right? So here we have 16. We have m equal to 16. See, we have m. Our m is 16. So we have n tuples. The size of n tuple is log 2 to the base log 16 to the base 2, which is 4 bits. So the size of our n tuple is 4 bits. The size of our n tuple is 4 bits. Now we can map this for, suppose for the first 4 bits, which are 1 1, first 4 bits we have, these are the first 4 bits of this sequence. Suppose for the first 4 bits I select a signal. This is 1110, right? So suppose for the first 4 bits we transmit this signal, right? This signal. Suppose for the this is the symbol corresponding to the first 4 bits represented. So for the first 4 bits we have this symbol. Now if you see this symbol, it will have 2 coordinates, the image of this over x-axis and the image over y-axis, or we can say AI1 and AI2, and both of these AIs are negative, right? This is negative, this is also negative. Both of these are negative. Similarly, for the next 4 symbols we may choose another. For the next 4 bits, so we have if you go to the next 4 bits, suppose we have these 4 bits. So next 4 bits are 0011, and for the next 4 bits, suppose we choose another symbol, which is this one. Suppose this is the symbol which transmit these 4 bits, 0011, right? So if we observe here, we have 2 again AI, its 2 coordinates, x and y coordinates. One will be positive, right? X-axis is negative and the other one is positive. So we have AI1 and AI2 similarly for the second symbol. So this is suppose this is our first symbol to be transmitted, S1, and this is our second symbol to be transmitted, S2. Now for these S1 and S2, we have now what can I do? Let me write it specifically. When I have to transmit S1 of t, my 4 bits, my S1 of t would be AI1, which is negative, right? Instead of I, now I can write A11 P of t, right? And my S2 of t, keep in mind this is not the this S1 and S2 are different than the symbols. Don't mix it with these symbols, right? Let me give it a different name. Instead of writing S1 here, I would say X1. So let me choose different symbols. Let me choose X1 here. Suppose this is X1, this is X1 and X2. because I use the these S1 and S2 here also. If you see here, I use S1 and S2 to represent these components, right? So this S1 and S2, S1 and S2, don't mix it with this S1 and S2. These are the these S1 and X2. So if we observe the S1 and S2 here, these should not be mixed with those QAM symbols, because these are just the this is actually your QAM symbol. Now I'm taking it as X. I'm taking it as XI of t, right? XI of t. So that it is different from S1 and S2 here. It is different from S1 and S2 here, right? So this should be this should not be confused. So let's go there and see our symbols. Suppose we saw that, okay, we have two symbols. We have data 1110 and 0011, and we transmit X1 and X2 for this. Now for the first symbol, X1, for the first symbol, these are for X1. If we want to transmit X1 of t, we have S1 and S2, and S1 is this one. S2 would be that is also negative, which is the second, which is the image of the first X1 of t. So this subscript is for the symbol over the second axis. So we can write it this way. So similarly for X2 of t, if you want to transmit X2 of t, the second 4 bits with that symbol, you will have S1 of t is this is negative, right? So now your S1 of t is this is for the second symbol. So 21 p of t. We are using the same notation. Similarly, your S2 of t would be the image of the second, this is positive, the image of the second over the second signal over the second axis, or over the sine 2 pi fct. So you can see, you can observe that our AIs, which are these may be negative or positive depending upon the symbol you transmit or the signal you transmit. So these may be negative or positive, and we can generalize it. Instead of writing it this way for each one, we can simply rewrite this in a more compact form, and we can say that, okay, we can let me rewrite it here. We can say that our S1 of t in general, this is for the second time interval, right? This S2, this one is for the second time interval. This one is from t to 2t. I should write it specifically. T to 2t, right? The second symbol we transmit in the second time interval. So x2 of t we transmit in this interval. Now instead of writing it for each interval, we usually we would like to have a generalized expression. So we can say that, okay, our S1 of t can be written in this form: a I1 p of t minus I t. Similarly, we can say that, okay, our S2 of t can be expressed in this form as a summation a I2 on the second axis. This is the image on the second axis, and let's see. Now you can compare it with those two symbols. Suppose you have only two symbols. So for all I means just for two symbols. For all I, what will be our S1? if you see our S1 for just those two symbols, our S1 would be, let me write it here, S1 would be A11 first symbol, P of T, right? And then we will have a second symbol, A21 P of T minus, okay. This is for the next time interval. So in the first time interval, S1 is A11 P of T. In the next time interval, it is A sub 21 PT minus. Now what would be S2? S2 would be similarly A12 P of T plus this is for the S21 with, in the second interval we are transmitting second symbol, so this one is the interpretation of a symbol. So A21 P of T minus capital T. Now if you compare this expression, with your if you compare this expression with your previous now whatever we discussed, if you see your x11, your x1 of t, when we transmit x1 of t, this x1 of t requires the transmission of a11 and a12. It's to in the first time interval it requires the transmission of these two coordinates a11 and a12, and actually both of these are negative. A11 is negative and A21 is negative, which we just saw in the previous slide. Similarly, if you want to transmit the next for the we transmit this for the bits 1 1 1 0, right? These bits represent x1 of t. Similarly, when we transmit 00 11, we need to transmit x2 of t, and the symbols which will be transmitted in the second time intervals are these one. Actually the coordinates are a21 and a22. These we need to transmit, and actually if you see the sign of these a21 and a22, this is a21 is negative and a22 is positive, right? So we need to transmit these. Now here, depending upon the size of this, the sign of this a11 and a22, we sum up our signals. We sum up our sinusoid signals, but the sign, these signs would be used. These signs, the signs of actual numbers, the signs of these actual numbers would be used for transmission. So if we go back to our diagram, so let me show you that diagram here. Let me bring back the diagram. These are our constellation which we need to transmit. Now if you see over here in this diagram, let me bring it on the screen. I need this expression as well. So if you observe this diagram with this expression now, it's very easy to see that we initially when you receive some bits here, right? So you receive some bits. For example, as the bits which we discussed were 1 1 1 0. So let me rewrite it. Correct. The bit which we just discussed, that okay, this is our 1 1 1 0, and the next 0 0 1 1. So whenever these bits are received here, the level, you have a level generator in the diagram. The level generator would choose AI1 and AI2, right? The level generator would choose AI1 and AI2. As I just said, that for these 4 bits, the level generator would choose AI1 and AI2. So AI1 and AI2 are negative, both are negative, right? And there should be, of course, these are some numbers. These are numbers which I'll tell you later on that what actually these numbers are. So these are actually the numbers, right? Because the coordinates, so coordinates are, these are real numbers. So based on the data, the level generator would choose these numbers, right? And then in the upper branch, if you observe closely the upper branch, in the upper branch we would have the first this one, which I can write AK1 using the same notation as in your book, and here it is AK2. So I or K, these are just subscript. You can for the first symbol we have we move for just K. K is just an index, right? So this just represent the symbol number 1, symbol number 2, symbol number 3, and so on. So the first AI1, it goes here in the upper branch, and the second AI2, which is selected by this level generator, goes to the second branch. Now if you observe your expression, what we said, that our S1, now we have to generate in the upper branch. Let me concentrate on the upper branch, and then I'll explain the lower branch, right? If you observe your expression, what we do, we multiply here, just okay, I need this diagram now. We multiply AI with P, right? AI with P of T, and then we will AI1 with P of T. So we already selected this AI1, and it moves to the upper branch. Now with this knowledge, it will be multiplied with P of T, and this AI P of T, what happens, this AI P of T further bring it here to the center of the screen. This AI P of T is multiplied with cos of 2 pi f ct. So if you observe, your S1 of T is then multiplied with this one. So in the upper branch, we are generating this signal from the upper branch, and the lower branch will generate the other half part. So AI P of T, so we have from our diagram, if we observe our diagram now, it means here we have P of T, which is actually multiplied with AK1. So this would be, the product would come over here at this point, and this product is then multiplied with cos of 2 pi f ct. We have an oscillator. Oscillators give us cos of 2 pi f ct, right? So this is actually multiplied with the upper branch. Now here you can see from this output, this is cos of 2 pi f ct and AK1 P of T. So you will get the upper half signal from this branch. The lower half you can see now. You can see AK2 comes to the lower branch. Let me choose a different color. AK2 comes to the lower branch. So here we have AK2. P of T, again P of T will be multiplied with it, AK2 P of T, and then we have from the oscillator we need, if you observe your signal, from the oscillator, actually we need just a minus sign of T here, right? We need minus sign of T. See this term. So this pi by 2 shifter is available in the diagram, which shifts the oscillator the output by pi by 2 radians, and we get minus sine 2 pi fct here, minus sine omega ct, right? Minus sine 2 pi fct. This will be multiplied with a signal coming from this branch, which is the product, right? Now, if you observe your signal at this point, you get this one. You get this signal. So these two signals, minus S2, this is actually S2 of t is coming from here. S2 of t is coming from here. Minus S2 of t, sine of 2 pi fct, the oscillator, it's the product multiplied, and then this is added up with the signal coming from this branch, which is according to this expression. You add this one and these two. You just add these two parts. When you add it, you get a signal QAM modulated signal xi of t. QAM modulated signal xi of t, right? Is your QAM modulated signal xi of t. So this is how the modulator works. Now I would like to show you the code example. Now you can just try this one for the second symbol as well, because we tried this data. So we can just try, just level generator will choose a different AIs, right, based on this data, and the same process happens. You have to generate S1 of t, S1 and S2 of t, and your S1, if you observe, this is your S1 of t here, right, and this is your S2 of t here. So these are the two parts which are multiplied with these sine carriers, and you get finally you get the QAM modulated symbol. So this is how the QAM modulator works. With this QAM modulation, now let's move to the code. Well, before moving towards the code example, let me show you another. Let me clarify another point over here, which I just mentioned in the end, because you selected two symbols, right? So we said that those two symbols we can write in this form, right? This summation. We can write those two symbols as these summations, right? And with this summation, we already saw that, okay, this is the first this is the first S1 and this is S2. Now we just, whatever we did just now is only this part. We just from the upper branch we generated this one and this one in the first time interval from t between 0 to capital T. In the next time interval, you now the first time interval, this is we take this one 0. This is 0 because we have P of t, right? First time interval, we have P of t, or you can say that you are transmitting x naught of t, right? So to be consistent with this one, let's choose instead of to be consistent with this one, and so that you do not confuse with this selection of I, let me clarify, because when you later on you go through this and you will say that we just choose S1 and I was 1 there, and here it should be from P to T. So just change this one. Suppose we are transmitting for this symbol, we are transmitting x naught of t, so I is not 0, right? And we are transmitting x1 of t. Here you can write x1. Just write x1 of t. This is x1 of t when we transmit these bits. So the first x naught of t. When you say x naught of t, you will have I naught, right? You will have I naught, and this will be you will have I naught for the first one. Now you can this I will be okay, because you will have S1 and S2, and the first symbol is this one, not. The second symbol is 1 here. The second symbol is 1. So when you have I equal to naught, you are transmitting x naught of t. The first symbol is its rectangular parts are a naught 1, a sub naught 2. These are the for the first symbol. So you will have p of t, p of t. For the second symbol, you are transmitting x1 of t, so I is 1. So you will have a11, so this is this should be a11 and a11 and a12. This is 2. This is 2 here. This is 2 here, right? On the second, no, we just let me clarify it. This is for the a01 and a02. Similarly, a11 and here it should be 2. Here this should be 2. This should be 2. This is the image on the second, second axis. So this should be 2. So you can see now it's consistent. You will not be confused with this I, right? So for the first symbol, you take x naught of t, and the second symbol is x1 of t, and then these expression you can generate s1 and s2 for 2 symbols. Similarly, you can go for move for I1 not 1 2 3. You can have as many symbols, and this will in the s1 and s2 can be generated using these expression. So there will be no ambiguity now. There will be no ambiguity. Okay, we will in the next example we will see the code, the octave code running the octave code for this QAM modulator.